Yes, please.
Okay, so welcome everyone to another KUIS AI Talk. And this week we are very happy to host Professor Noah Snavely. And Noah is a professor at Cornell Tech, and he's also a research scientist at Google Research at New York City. And he has done amazing work in computer vision and graphics. He frankly does not have an introduction in the computer vision community and has done lots of fundamental works in structure for motion, 3D reconstruction, and 3D vision. And I mean, in fact, two of my last papers were actually inspired by his great work, and especially in my last paper, his team at Google helped me a lot from the dimensional motion paper, if you remember. And Noah is the recipient of Microsoft New Faculty Fellowship, a SIGGRAPH Significant New Research Award, among many other awards. So we are really looking forward to your talk, and this stage is yours.
Cool. Thank you. Thank you so much. I'm sharing my screen now. Thank you for the very nice introduction. So yeah, it's so great to be here. I'm so happy to talk to you all. Thank you so much for inviting me. And so yeah, I'm going to talk about, I don't know, if you had access to all the world's videos, what kinds of models of predicting 3D shape and motion could you build? Okay. So video is old. Video has been around for a long time. In the old days, video was called moving pictures, and you'd go to a theater and see it, like this moving picture here. This is a famous moving picture of the train arriving at the station. I think this was one of the earliest films screened to an audience in a theater, and the story was that the audience was so scared by the prospect of a train coming at them that they ran to the back of the theater. Now I think that might be a legendary, a apocryphal story, but it speaks to the very compelling illusion of motion and of shape that you get from a sequence of rapidly projected images. Okay, and intuitively that should be true for computers too. We should be able to build computers that can understand motion and 3D and just totally understand everything that's happening, all the 3D shapes and all the motions that are happening in this video. Okay. Here's a more modern video. This is a video of a drone flying through a house. It's like a real estate kind of video, like you might find on a real estate site. And again, so in this case, well, first of all, you can imagine taking 3D computer vision methods and estimating the beautiful 3D model of this home from 3D methods. Like you could do a fly through of it. But if you had a million videos of a million homes, you could probably go further. You could learn to generalize. You could probably take a single frame of this video and predict, a depth map or even, a 3D model of the entire house. If you had all videos of all houses, you could probably generalize. You could use generative techniques to imagine and synthesize new homes that don't exist. So again, video seems like a very good source of data for learning about the world, learning about the 3D shape and generalizing to new scenes. Okay, so here's an example of a actual problem you might want that you might want to solve. This is a problem I've thought about for a long time, where I think video might be an important ingredient to solving it. Okay, and it's sort of like the im to scene problem. The goal would be to take one or more input images, maybe just even just a single image, like this one shown here, and somehow predict a beautiful full 3D scene, complete 3D scene, even the parts of the scene you don't observe in this image, in beautiful detail, very accurate geometry, realistic materials, and in a format that you can easily do things like edit and relight it. Okay, so image to full, complete, useful 3D model is the problem here. You could also call this inverse Pixar, because Pixar is in the business of doing the opposite. They build Pixar and all of the 3D animation companies. They build beautiful 3D models. Maybe it takes a lot of artist time to build those models and of scenes and characters, and then they put that in a graphics engine and render the image like this one on the left. So they go the opposite way. It would be nice if we could go the direction of taking an image and infer the model. But this is a very difficult problem. It's very difficult because it's a super ill-posed problem. There's many different 3D scenes that could explain this image. But it's also, that wouldn't be such a problem if we had training data. Like if we had billions of examples of training scenes, we could still learn this. But the problem is it's very difficult to get training data. You know, Pixar just doesn't release their, Pixar is not very, is not known for releasing all their 3D assets to the community. It's very difficult to get super ground truth 3D models with good material properties and realistic texture maps and all that. Okay, so it's very difficult to directly supervise this with the direct ground truth. But I think there's hope for using video as the training signal for this kind of problem. And you've seen, actually, we're seeing this more and more in this generative AI world we live in. I'll talk about that in a minute. But a very powerful training signal that's much easier to get is a view synthesis training signal. And the view synthesis training signal works something like this. You take an image, you have some kind of network that predicts a scene in some format, like a mesh. And then, okay, how do you train it if you don't have that ground truth scene? Well, you can render a new image from a different viewpoint. And then if you happen to have that view, because you had multiple views of the scene, then now you have a training signal. You can compare this rendered image to the ground truth image. And if they're different, that gives you a loss you can use to back propagate through this whole, if you have a differential renderer, you can learn, it's a signal for training this scene predictor. Okay. And now there's just like a few missing pieces. There's, okay, what do you use for the scene description? And there's lots of options. You could use everything as simple as a depth map to, full nerf description of the scene and so on. And then the only other ingredient you need is lots and lots of pairs of images of the same scene, across many different scenes, but for each scene you have multiple images from different viewpoints with known camera poses. Okay, and if you have that, at least in theory, you can train something like im to scene from with a differentiable renderer, as long as you can back propagate all the way through this process. Okay, so we've taken that and said, okay, well, if the way to train like the world's best 3D reasoning modules is to get frames from multiple viewpoints, maybe we could do that with video. So for several years now, I've spent time looking at YouTube, watching videos, trying to find examples of this kind of data online. Okay, so the specific kind of data you want for this kind of training is, videos which feature static scenes, okay, because we don't know how to deal with, I'll talk about how we deal with moving scenes in a minute, but for now, static scenes from moving cameras. Okay, so you want camera motion, but no scene motion. Okay, and so we over time found a bunch of different genres of videos. Like that turns out real estate videos are very commonly have that character. For some reason, real estate videos don't often feature people in them or any other moving object, maybe because you're supposed to imagine yourself in the home. We built a data set from real estate videos. There was this funny genre of YouTube video for a while, maybe several years ago, called mannequin challenge videos, where it's people intentionally standing like statues. So that's another kind of video where static scene, moving camera. Drone videos of nature. So if you restrict yourselves to static scenes and moving cameras, you discover that there's kind of interesting genres of videos that you can perhaps learn from. So I'll show you an example of this. So first of all, though, we also need the camera poses. So at Google, we also built a scalable pipeline for basically running SLAM, which is a way of doing camera trajectory estimation, estimating the camera pose at each frame of this video from video at scale. Here's the output of our method, which is built on a popular SLAM simultaneous localization and mapping pipeline called OrbSLAM. So you put a video in and you get a camera trajectory and a sparse 3D point cloud of the scene out. Okay, and we can run that on millions of videos and get hundreds of millions of examples of frames where you have, they're taken from the same scene, but from different viewpoints and with known camera poses. Okay, so that's great. One such data set we built is called Real Estate 10K. It's just based on mining real estate videos, which are very common. People love seeing videos of homes that they want to maybe buy or at least aspire to buy. So this is about 10 million frames taken from 10,000 videos. with known camera poses for each frame. And with that, you can do, you can do a lot of things. With a data set like this, you can do something like train a method that can take a single view and synthesize new views from that single view. Okay, so here's some examples from a paper a few years ago where, here's single images, and then you can estimate some kind of geometric model that then allows you to render new poses. And it is also, because it's seeing examples of like shiny objects, it can render reasonable like reflections and stuff too. You can also kind of get a depth map from this. And this is not trained with depth maps as supervision. There's no depth maps. It's never seen a depth map of training time. It's just learned about 3D from the basis of being supervised with multiple views of scenes. Okay. The specific kind of scene representation, okay, because you have to choose what kind of scene representation you use. For this project I just showed is called a multiplane image. And a multiplane image is a very kind of simple scene description inspired by actually old like ways of doing 2D animation, which consists of a set of RGB alpha images. So you have RGB images with transparency stacked in a big stack, such that when you look at them from the right vantage point and move your head, they kind of create the illusion of 3D. Okay, so I'll just animate that so you can see what it looks like. But it could be any scene representation. Multiplane image is just a convenient one. So the method I just showed takes a single image and predicts this multiplane image, such that if you arrange it in 3D in the right way and view it from the right reference point, these frames kind of coalesce into a 3D scene like this. Okay. And like I said, this is trained using just a view synthesis objective. So you take your single input image, you have a neural net that's learning to predict MPIs from a single input image. So you get a single image and a neural network produces a stack of RGB alpha images that form your MPI. And from that MPI, you can render new views. And if you happen to have the ground truth like view from those new vantage points, because you took this data from Real Estate 10K where you have withheld views, again, now you have a training signal and you can backpropagate a loss. You can backpropagate this loss through the entire network and train your image to MPI. And that works really well. You can learn to synthesize new views even from a single image by training on multiple views. Okay.
Noah?
And yes, question.
Yeah, the previous slide,
Yeah.
Are you stitching those images together to construct 3D view, or what exactly you're doing, in terms of 3D? I'm trying to understand that.
Yeah,
Are you
so
stitching them together to construct the full 3D, or I don't see any stitching, but I'm trying to understand, when you say learning 3D, what exactly do you mean? Do you understand the question? Typically, when my understanding of computer vision is very limited, but it is you stitch the images, you construct the views from multiple range images or things like that, but you're not doing something along the
yeah.
line.
So that's what we do for our training data. So that's what's happening here. In the training to create the training data, we do this kind of reasoning across multiple views. We match feature points, and then we reason about the camera poses from those feature matches. Okay, and then you get these camera poses, and so that's what the training data looks like. But then we throw away these point clouds. We only use the camera poses, and the way this works is when we train this network, this network only gets to see a single image. It can't possibly stitch multiple images together to reason about 3D. It's only seeing a single image. So there's no reasoning about multi-view geometry. What it's trying to do instead is take the pixels and predict, okay, I think the shape of the scene is this. It's trying to predict essentially something like a depth map from a single image. And the way it's trained is by, okay, taking the training data where we have stitched multiple views together and using that as a kind of supervision. Okay, so one way you could think about it is from our training data, we could also reconstruct a depth map for every frame, because now that we have 3D camera poses, you can compute like a per frame depth map using stereo. And then you could use that data. Now that you have a depth map per frame, that's data you can use to train a image to depth map, single image to depth map regressor. Does that make sense? So you're using 3D to create your training data, but at test time, you only get to see a single view, but hopefully the 3D you can kind of generalize from the 3D that you've created in your training set. Does that make sense? That's
Yeah,
the idea.
kind of like as if that you are rotating the camera, right? Is it?
Yeah, it says you learn how to create what that rotation would look like,
Yeah.
but only from a single image. Because you've seen it so many times in the training data, you can start to learn to predict, new camera motions from single images, if that makes sense.
Yeah, that makes sense. It's an interesting idea.
Yeah. And this idea is also I think it's interesting too. It's also becoming quite popular because there's these methods that are doing this with diffusion models. So basically, starting with a paper called 3DIM, they're using view synthesis as a training signal for diffusion models. So basically, the way this works is you take an input image that's shown at the top here. You give it a camera pose and say, okay, like I want an image of this object, but from this viewpoint. And they learn a diffusion model that conditioned on a image and a pose predict a new image. And if you can do that, you can generate all the images of that object and coalesce them into a 3D model. So you can do single image to 3D shape trained using view synthesis. You never saw a 3D shape. The 3D shape was not shown to the network at training time. All it saw was an image, two images at training time. It's the image that it takes in and the image used to compute a loss. People may have heard of this very popular method called 0123 released recently, which does the same thing. It takes image and a relative pose and predicts a new image from that pose. These were trained, 3DIM and 0123 were trained on synthetic data. So they rendered, 3D objects from this Objaverse data set or other 3D data sets. But you can also do the same thing with real data. If you have lots of videos with known pose for each frame, you can use that to train a image to object model using a view synthesis loss. Okay. Are there other questions about this before I move on? I'm happy. Yeah, please. If there are any questions, please feel free to interrupt me.
Again, like, I mean, in the past, there was a concept called image-based rendering. Like,
yeah.
Do you how is it compared to that? Like, there is an intelligence in here, I guess, like compared to those image-based renderings earlier developing computer vision, is it?
Yeah, it's a good question. I mean, image-based rendering, the classic image-based rendering requires, lots of images. So you don't need to compute the 3D model, but you need as input lots of images from lots of different viewpoints. And then you can interpolate between them to fill in the missing viewpoints. Here, the big difference in these modern machine learning days we live in is you only need a single image. And you can do essentially image-based rendering from that single image. Like these methods, you can give it the front of a chair, and it can predict the back of the chair from that single image. Okay, so it's like it's very much like in the spirit of image-based rendering, but you only need a single image because it's really good at predicting what new views will look like from that single image.
Cool. Very cool.
Yeah.
Thank you.
And by the way, none of these papers are my work, but this is the very recent 3D. This is kind of like I guess the name for this field is 3D generative modeling and things like that. But yeah, very much using the same kind of tools that I've been working on, this view synthesis kind of loss. Okay, sorry. Any other questions before I move on?
I was going to ask, is diffusion models, for rendering images, do they also work for like indoor images? Because here you're also only showing like objects from different cameras looking at it.
Yes. Sorry, go ahead.
Have diffusion models been successfully used for like other, like not these like an object, but like big scenes, driving scenes or like indoor scenes of like real estate data sets?
Yeah, to some extent, yes. So like this Zero NVS paper, which just appeared on Archive like maybe a month ago or less, they also train on Real Estate 10K. Real Estate 10K has kind of become like not at the scale, but it's sort of like a what do you call it? The MNIST sort of like 3D data sets. So a lot of people are training on it. It works kind of well, but I don't think it can't generalize in the way that you might hope. So like the ultimate, scenes are just so much harder than objects. Like, imagine I gave you a photo of a kitchen. I just gave you an image of a kitchen, okay? And then I ask you to predict a completely different view, like 2 rooms away. Well, that room could be a bathroom, or it could be a bedroom, or it could be a living room, or, it's just much more ill-posed, even compared to, predicting the front of an object from the back of an object. So I think I'm very interested in this like scene level reasoning, but I think it's much harder and will require much more data, much bigger than Real Estate 10K, for instance. I think it's possible, but I think we're not there yet. These methods can't really do like full scene level reasoning. And yeah, the 0, 1, 2, 3, indeed, that's only trained on objects. In fact, it's only trained on objects with like blank backgrounds. So it can't even reason about what the background is going to do. Does that make sense? Okay. Good. So, another big limitation of everything I've showed so far is that, nothing's moving. These scenes are completely static. But most videos are not like that. Most videos, even if the camera's moving, there's also things in the scene moving. Okay, this is a very kind of busy scene from the Chelsea market near where I work in New York City. And there's a lot of, so, okay, what happens if you try and, another way to put this is limiting to yourself to the set of videos of static scenes is a very limiting assumption. What happens if we try and use all videos? Well, the SLAM systems I talked about, they often break. Like orb SLAM might get confused by the object motion because it assumes like it's trying to track static geometry. And even more, you can't, like all the beautiful methods we've developed in 3D computer vision kind of go out the window once things start moving. And the reason is the difference, in essence, the reason why 3D methods start failing, all the beautiful like 3D theory we have starts failing, is the difference between statues and people. Okay, if you take a statue like the Statue of Liberty and you view it from different angles, the pixels move around, but they're moving around in a very controlled way, such that if you take the same point in 2 different images, like the corresponding point on the top of the torch, that these are projections of the same 3D point in the world. Like you could attach a GPS coordinate like, lat, long, and altitude to this 3D point, and that point wouldn't change in different views. Like that's a constant, modulo, like, I guess, the drifting of continents by a few centimeters every year. But in all practical terms, this is a fixed point. Whereas with people, okay, you might take an image of a person and you take a similar point on the top of their hand here, and then you take another picture maybe a few seconds later, but by that point, that point has moved in 3D. It's no longer a projection, even though these points are in correspondence, they're no longer a projection of the same 3D point in the world, because that point has moved, because this is not a static scene. Okay, so we can't do things like triangulate anymore. Triangulation goes out the window because these rays no longer intersect. All the things we want to do in 3D don't work. Okay, so you can try and bandage over this. And I mentioned this this mannequin challenge data set. You can try and bandage over this and learn about people by finding videos where people are static, like mannequin challenge videos where people are intentionally behaving like statues for fun internet points. And if you take videos like this, you can find a lot of them. There's thousands of videos of people acting in this interesting way, with all sorts of diverse scenes and diverse poses. And you can build a data set of that. This is the work of my PhD student, Jung-Chi Lee, that appeared at CVPR a few years ago. And again, the nice thing about this data is that because the people are not moving, here I'm showing depth maps, like I'm fading in between the RGB and the depth. You can run SLAM and you can get depth maps, and you can get like ground truth 3D geometry, even though these people are moving, even though there's people. And it's because the people are static. If the people are moving, then you wouldn't get good depth maps because you can't do triangulation and things like that. Okay, and once you have that data, you can do very simple things like learn to predict depth for people and apply that to videos where people are moving, because now you just have a very good single image prior over depth of people. Okay, so we did all sorts of things with video applications of this work. Once we have lots of data with ground truth 3D, you can train all sorts of 3D reasoning methods for videos of people. Okay, but that's really just a band-aid. Like we got lucky that there was video of people standing still. And maybe we wouldn't get so lucky if we want to scale this to all possible scenes. And plus, you want to learn about motion. You don't want to just ignore motion. Motion is such a fundamental part of the world. So learning 3D from like these specific static scene videos is great, but it's very limiting, right? We want to learn about, we in some sense, for convenience, we're trying to keep it simple and just stick to static scenes. But well, there's so much more we could do if we could use all videos. So I don't know, like the world is just so rich in terms of its motion. It'd be great if you could have a computer that just observed all the world's video and could learn like physics, like learn how humans behave, learn human dynamics, learn ballistic motion, it'd be really cool if you could have a computer that just observed all video and learned and could come up with like Newton's 3 laws of motion, right? And for that, you need to embrace motion and learn about it. And I think if you really wanted a machine to do this, you need to first solve the problem of very low level understanding. You need to take videos and, just like humans can do as we move around the world, derive full descriptions of the 3D shape and motion as a kind of training data for reasoning about motion in real world scenes. Okay, so okay, I'm sorry, I have to take a quick I forgot that I don't have this room booked for for the whole hour. Let me just sorry, I have to move really quickly. In the meantime, do you have any questions while I quickly relocate? Okay, sorry about that.
That's okay.
Yeah, sorry, this is Google where I'm situated now. Sorry, really sorry about that. Okay, so yeah, just to set the stage again, what we really would want is a method that can take a video and estimate complete 3D, complete motion. But that's a very hard problem. So if you want to take a monocular video from a single viewpoint, like this one, and estimate the 3D shape of every pixel, well, everything kind of goes wrong. So the thing you need to start with, camera poses, they're very hard, they're annoying to compute because SLAM methods get confused if there's motion. And even if you had camera poses, you can't really use 3D methods because of this statues versus people problem. They all assume that the scene is static. Okay, so instead, well, let's start by a simpler problem of estimating 2D motion. Okay, maybe we can at least estimate full 2D motion. And if we can estimate 2D motion, maybe somehow we can upgrade it. There's used to be popular like methods called non-rigid structure motion, but that requires like you have at least 2D correspondence between all frames. So what I mean here is we'd like as a starting point to, for every frame, compute correspondences. So, the foot should be in correspondence in all frames. Point on the swing should be in correspondence, point on the head. We want a full description of all the correspondence in this video, all the 2D motion in this video. And it turns out that surprisingly, that's not really a solved problem. there's things that are in computer vision, motion tends to be estimated in two different forms. The first is sparse feature tracking. Okay, so here I'm just showing like illustrations of motion. And for simplicity, I'm showing like, okay, imagine you have just a single dimension of your image, of your video, spatial dimension X, so, and a time dimension. And here I'm showing an illustration of sparse feature tracking. So sparse feature tracking is, for a set of points that are easy to track, like corners of things, track long-term trajectories through the video, okay? Along this time dimension. Or another very popular kind of motion representation is optical flow. So optical flow says, for every pixel in every frame, estimate its corresponding point in the next frame. But it does that independently for every frame. So there's no kind of coherent motion. There's no long-term estimation of motion. It's just motion between pairs of consecutive frames. Okay, so these are the kind of two classic paradigms. What you really want is dense motion like an optical flow, but long-range motion likens feature tracking. So it'd be really great if you could compute for every pixel its motion throughout the video, throughout the entire video. And if you start doing that, you have to, all sorts of problems come up. Like you also have to be able to track through occlusions. So if an object passes behind another object, you still want to maintain the correspondence when it reappears. And you need to be able to handle large deformations. Like if a person is doing jumping jacks, their hand might look very different because in different poses, but you still want to track it anyway. Okay, so that was the basis of that problem is the basis of a recent work that appeared at ICCV, led by my PhD student Chen Wang, who's now a postdoc at Berkeley, and that got a student paper award at ICCV called "Tracking Everything Everywhere All at Once." And I'll talk about this paper in a little bit more detail until I have to stop. So again, the problem definition here, just in a little bit more granularity, is given a video sequence, a sequence of frames, for every pixel XY in any frame, estimate the corresponding location in any other frame. Okay, so in other words, full length trajectories for every single pixel in the video. Okay, that's the problem. It sounds pretty clear, and I think surprisingly it's unsolved, and maybe it's not so surprising because it's a very difficult problem. Here's just an illustration of the output of this method. Here's a video, I'll play a video of this horse, and you can see the point trajectories are very coherent and long-term. So I'm showing kind of the pixel motion as these motion trails over time. I'm only showing it for a sparse set of points because if I showed it for every point in this video, it would get very confusing. But indeed, for every point in the video, whether it's the foreground or the background, it's tracked throughout every frame. Okay. If these videos don't come through very well in Zoom, you can look at the webpage, which has a lot of like rainbow colored videos like this. Here's a few other examples for different scenes showing different kinds of motions that are tracked, where the motion is tracked coherently over long distances. Okay, so if you want to solve this problem, you have a few different things you have to think about. One is, how do you represent this motion? If it's not optical flow or sparse feature tracking, what's the data structure even that is used to store this motion? Okay, and then once you've decided on the data structure, how do you compute it for a video? Okay, so let's talk about the representation first. And just to set the stage, there's this problem of long-range motion has become pretty popular recently. There's a couple examples of work that's sort of gotten a lot of attention. One is called TAPVID, which is a benchmark. It presents a benchmark for doing this, for evaluating this long-range motion. It turned out we didn't even have very good methods for evaluating this long-range motion problem. So they introduced a benchmark with lots of human curation of point tracks across videos, and also introduced a method for estimating motion. And then another is called Particle Video Revisited from CMU, which also does long-range pixel estimation. But both of these methods are not global, so they don't get to see the full video. And I think that's a I think that to really solve this problem, you might need to have a method that looks at the entire video in some way. There's also other recent work, one's called Tapir and one's called CoTracker and other things that also attack this problem. So the reason why I think global motion is important is that it's very easy to lose coherence if you're not looking at every frame of the video in your motion estimation pipeline. So, if a point is occluded, for instance, for a number of frames, and you're not like looking globally over the entire video, that occlusion event might break your motion estimates. So like here, I'm going to show a video with estimates from this particle video revisited, more local method versus our more global method that I'll talk about in a moment. And you can see that the coherence of the pixel trajectories is much higher in our global method. Some of the pixels are sticking to the background once it goes behind the, this person on the swing is going behind this pole, and points get all discombobulated in, through that occlusion. Okay, so we want global motion. How do we store it? How do we even represent it? And the way we do it is with a very popular kind of method these days, which is we represent the motion as a neural network, and in particular as an MLP. Just as, if you know about methods like NERF, they represent scenes in MLPs, we're going to represent a motion in an MLP. And the way this is going to work is that if you take a frame I and you want to estimate the corresponding pixel for a 2D pixel XY in that frame, in another frame J, you use that XY location as an input, and you also have some side inputs. The input and output time are side inputs to this coordinate-based MLP. It's called coordinate-based because it takes in literally the coordinate you want to map to another frame. And it's supposed to output the corresponding point in the other frame. And it will be trained to do this. So once this MLP is trained, what it should do is produce accurate correspondences that allow you to map any pixel in any frame to any pixel in any other, to the matching pixel in any other frame. Okay, so I guess for now, it's just this magic MLP that somehow gets trained to do this. And if you do this, okay, that's nice because it's global. It stores all the correspondences in one data structure for every frame to every frame. You can track any point, and it's also in some sense compact because it's a single data structure. Maybe it will have a lot of parameters, but maybe it can at least be succinct and parsimonious because it's all stored together. Okay, but you immediately run into some problems if you try to do this. Okay, so first of all, let's look at what happens. Okay, maybe you want to track a point in this frame to the second frame. You can do that. You can just, it's able to represent this very easily. You give it a point, you get another point in the second frame. But what if you want to map this point back to the first frame? Well, the world should have bijections or one-to-one invertible mappings between each frame, but there's no guarantee of this in just a vanilla MLP. If I try and do the inverse and put in this pixel in frame J and ask it the correspondence frame I, maybe I'll get a different point. There's no cycle consistency, okay, which should be a invariant of the world mostly. I mean, if I take my hands and put them together, I guess now there's some points that maybe it's not fully invertible, but for the most part, you want an invertible mapping between frames. Okay, another problem is that if you map a point into another frame that's occluded in that second frame, well, that's fine. You can still say that this point should map to where the feet are, even if the feet are hidden. But then if you try and map this to another frame, a third frame, well, if this point should be the feet, then it should map to the feet in this frame. But this point also needs to represent the motion of this pole. So it also simultaneously needs to map to 2 points, okay? So any point which is has multiple surfaces at different depths, where you can only see the first surface, well, it still should somehow represent the motion of all of those points, okay? But that's, now we're not talking about a function anymore because there's 2 answers, okay? So this simple thing can't track through occlusion. Okay, so the observation here instead is that there should be a bijection, meaning what we want is a one-to-one and onto mapping between 3D points in a pair of frames, okay? If a scene is topology preserving, there should be a bijection, a 3D bijection between points in pairs of frames, in any pair of frames. Okay, so a bijection will give us cyclic consistency for free, because if it's bijection, that's just a property of bijections that they are invertible. Okay, and so we want the key thing. Okay, we want it to be 3D. What does that mean? We'll talk about that. Okay, and bijection, how do we get that? So we need to talk about how we arrive at these two different properties of the method, 3D and bijections. Okay, and if you can work in 3D, you also get occlusions for free. If you can somehow assign a depth to a point, now you can reason about multiple points that project to the same pixel, because you can assign them different depths. You can assign the close point one depth and the further point another depth. Okay, so taking all this together, we invented a method called omnimotion, which is essentially a method, a data structure where we represent bijective mappings from every frame of this video, every local coordinate frame to a canonical frame. Okay, so, and these are 3D mappings. So you imagine each video gets its own little 3D kind of model of the world. And there's bijections that map that 3D model to a canonical space, which is 3D in the number of coordinates, but it's quasi 3D because it's not really representing like accurate 3D geometry. It's just 3D because we need 3D to have enough space to store points at different depths and that are occluded in the scene. Okay, so we have this quasi 3D canonical space that we optimize with bijections between it and every individual frame. Bijection, again, just a invertible mapping from every frame to this canonical space. Okay, so we need a way to ensure 3D bijections, and we need some way to formulate what this 3D canonical space should look like. This kind of orangish pinkish cloud here. What is stored there? Okay, so let's start with the bijections. And so bijections, it turns out, there's been a lot of work on invertible neural networks in the past 5-10 years. Okay, so networks that you can run them both forward and backwards, and they're invertible. So if you put a point X in and get an output Y, then you can put the point Y into the inverse function. You can kind of run the neural network backwards and get back X. That's not a property of most neural networks because of things like ReLUs that destroy invertibility, but you can build special purpose neural networks that have this invertibility property. And one such kind of neural network are called coupling layers. I won't get into details, but with a coupling layer, you can pass a point through an invertible network, invertible MLP, and get a point out. And then you can pass that point back through the invertible network and get, you can pass a point through this invertible network and get a point in canonical coordinates. And then you can pass that point back into the invertible network, run it in reverse, but put in a different time step and get a point in another frame's local coordinate frame. Okay, so this canonical volume allows you to transfer points in an invertible, in a reversible way from one frame to another frame. So you first map a point to this canonical space and then map it back to another frame J. Okay, so good. So that's the way we represent mappings between frames through this canonical space. There's one more ingredient. Oh, sorry, I just saw there's a chat message. Oh, yeah, sorry, someone has to leave. Yeah, thank you for coming. Sorry, I'll try and wrap up soon. I'm arriving. Yeah, please.
How do we know that it is 3D in the sense that we understand 3D, because it's some just 3D space, right? It doesn't have to be necessarily something about 3D world. How do we assume that because it is the only common thing between frames?
Yeah, so you shouldn't have in mind that this will be a metric 3D reconstruction.
Yeah.
What it should be is it should get ordering right. So it needs 3D so that it can put stuff in front of other stuff. Okay, so at the end of the day, it needs to be 3D for that reason. But what you won't get is a like metric 3D reconstruction. You'll get something that's just qualitative in the sense that it should get the ordering between objects right. Does that answer the question?
Yeah, but can we prove that somehow? Can we show that it has this relative depth understanding somehow?
I'll show in a minute that there's no proof that. So in order to the idea is that the best way for it to explain the videos is to get the relative depth ordering right. There's no guarantee that it will, but the solution where it gets the ordering right should be better than the solution where it gets the ordering wrong. So I'll show some examples in just a minute.
Thank you.
Okay, yeah. So the other thing that we need is, because we need to know whether a point exists, we'll need to also assign for every point in the quasi 3D space a density. So, number between 0 and 1 indicating, is this point occupied or not? So there's also, in addition to these bijections, we have a density field mapping points in the canonical space to densities. Okay. So let me just put, so I've thrown a lot at you. The way that all these ingredients gets put together is as follows. Okay, so if I have a frame I, and I want to estimate correspondence for some pixel XY in that frame I, and I want to know where that point goes in another frame J. Here's how I do it. Okay, so I pretend I shoot rays through this local 3D volume. Okay, I gather a set of points along different depths along this point. So imagine I'm shooting a ray through this point, sampling points at different depths with that same XY location. Okay, so you can think of this as we're lifting this point to 3D. We have a set of different 3D points with the same XY coordinate but different Z coordinates. We map all of those 3D points to canonical space. Okay, so now we're talking about using our projection that we're estimating. We have points in canonical space, UVW, and we have n of them. We have n points, we've lifted it to n points in 3D. We're mapping them all to canonical space. Then we map all those points using this bijection back to frame J. So now we have a set of 3D points in frame J's coordinate frame. And because we are also reasoning about densities, we can retrieve the density for all of these 3D points. So now we have 3D coordinates with associated densities, and we can alpha composite them. So we're just as in methods like NERF, which are alpha compositing RGB colors along rays, we're alpha compositing essentially motions. We're taking a bunch of motion estimates and weights associated with each one, and we're combining them together into a single output coordinate. And then you just drop the Z coordinate. And it's sort of like in this pretend 3D world, we're using orthographic projection. You drop the Z coordinate, and now you have an estimated XY location in the frame J. So just it's a little bit complicated to think through, but the essence is we're using volume rendering to compute 2D motion estimates. Okay, so it's a way of using the volume rendering methods that have been developed for things like NERF in this 2D motion estimation problem. Okay, so that's our omni-motion representation. And sorry, I'm going to go a little bit quickly because I'm running out of time. I'm just going to say the way we optimize this, now that we have this representation, how we optimize this representation for a video is we take all pairwise optical flows between every single frame, like these pairs of frames, these pairs of frames, these pairs of frames. We use RAFT, which is a relatively state-of-the-art optical flow method, and we compute omni-motion such that when you use this rendered optical flow between every pair of frames, it should match the computed optical flow with RAFT. So another way you can think about this method is it's taking a bunch of noisy, independent local estimates of motion between every frame, every pair of frames, and globalizing it, optimizing for a single global representation of motion that best explains all of those local motions. Okay. I'll pause here for a moment in case there's another question. Actually, let me just show, let me just answer Fatma's question by showing a visualization. Okay. Here's if you optimize for a video of this person riding a swing, and you then use those opacities to render out a depth map, it looks something like this, okay? And you can see that this depth is not very accurate, okay? So like this pole, part of it is near and part of it is very far. Part of it is as near as this like foreground pole. But it's from a point of view of explaining the occlusion relationships in this video, it's correct, okay? So it's basically the best depth map you can get if all the information you have is just the occlusion rate relationships in the video, what's in front of what is in front of what. So it's sorting out the ordering of different layers of the video from the pairwise optical flow alone. Okay, so yeah, we've evaluated this. You can see like, it works quite well. I'm just gonna kind of speed through this. Even through things that deform a lot, you can get nice stable correspondences once you optimize it for each video. Here's another example where the camera's kind of zooming in. I'm also showing the pseudo depth map visualization, so you can see again, like it's getting the ordering of like the foreground and background objects right. It's getting nice stable correspondence. It does well in this tap vid benchmark, and it outperforms methods. It outperforms methods that reason more locally in very clear ways. So again, if you reason locally, like a very simple method is just a chain optical flow, and take pairwise optical flow and chain and just chain feature correspondence across many frames. That doesn't survive occlusions at all. All the points instantly kind of get glommed onto foreground objects when the object passes through occluders. Our method does much better. Okay, this video is even okay. I think my PowerPoint is starting to complain here. So yeah, I think I'll just wrap up quickly and summarize. So you can see all sorts of, we've run this on all sorts of videos. It works. It works quite well at handling a range of different cases. Let's see. Hopefully these videos will play. Okay, at least this one. Fast moving objects it has trouble with, thin objects it has trouble with, things where 2D motion, where sort of optical flow, things that are hard for optical flow will also be hard for our omnimotion method. Another limitation is the speed. So it takes, you have to estimate flow between every pair of frames. So it's this quadratic running time in the number of frames. It's also a test time optimization. So you're optimizing the representation for every single video, just like in methods like neural radiance fields. So it can be quite slow to optimize. But I really like this representation, and I feel like now that we have this kind of global representation for motion, we can start addressing these limitations. So it does well at producing accurate, dense global motion. It's very slow, so we want to scale it to long videos. But I think more generally, what I'm really excited about is the idea that if we can run something like this on every video in the world, then we can learn good priors over motion that we can apply in new instances. Okay, so I guess maybe one description of this, which is kind of like, I don't know, I'm not sure I like the word foundation model, but I'll use it because it's people kind of know what it means, I guess. So if you could train something that's been trained on all the world's video to understand motion, and so you have a very good prior over motion, I think you can fix a lot of problems in things like current text-to-video models. Like if you've seen things like these make a video, text-to-video methods, even stable video diffusion, they often produce unrealistic motion. They don't get the motion right. Things look uncanny and very strange in these like text-to-video methods. But I think if we can estimate long-range motion in videos, we can then learn priors over motion that will fix these kinds of problems. Okay, so I'll show a very, oh, sorry, this video isn't showing it all. Oh, here we go. Yeah, just an example of this that we put on archive recently is called generative image dynamics, where we learn a prior over just periodic or pseudo-periodic motions, which are very, it's pretty easy to estimate motion for videos where the object is kind of just vibrating in a stochastic way. And what we do is we take lots of videos of things vibrating and learn a prior that we can apply to single images. So we can take that prior and make this single image of a rose vibrate, or even interactively using methods developed by Abe Davis, interact with this single picture and see what would happen if we pulled this point and let it go. Okay, so this is just a very early work. This is limited to this kind of periodic or pseudo-periodic vibrational motion, but I think if we could understand motion deeply in all videos, that would be very powerful things for things like video generation. Okay, so I also want to say, yeah, Fatma mentioned Sadra's work earlier, and I think I think motion is a very good thing to be working on, and I really like some of the recent work from Fatma's group, and including Sadra's recent work on this problem too, because I also think this, motion and using motion as a signal to predict future frames, or using motion as a cue for training different methods, different ways of reasoning about videos. I think that's a really interesting and promising direction. Okay, so thank you for your attention. Thanks to all my collaborators on this work. I'd be happy to take any questions in the 1 minute we have remaining. Thank you so much.
Okay, thank you for the great talk. Does anybody have questions on the Zoom or here?
Thanks a lot, Noah. I have questions, but if there is anyone else.
Can I ask questions?
Okay, Sadra first.
In the exactly
Yeah.
in the liberal advanced paper, I mean, you show that the relative depth, is okay, but it's not that completely accurate. Can it be improved by using a molecular depth and regularizing the depth that you will get from your method, and try to improve the method using by adding depth regularization?
Yes, so actually Chen tried that, but it didn't work very well. And I think it might be that there's a mismatch, but I think that's a great idea. I think probably that's the right thing to do. I think we haven't figured out how to get it to work yet. I think maybe one problem is that the kind of depth predicted by the monocular depth networks is kind of incorrect in a way that is somehow incompatible with the depth that we need, or hard to reconcile with the depth that we're trying to reason about from occlusions. I don't know why that should be. It seems like monocular depth methods should be good at getting ordering right. So it's a little bit mysterious to me, but I think that's exactly right. Maybe the right thing to do is somehow train these two things together so that, the depth that's being trained with monocular depth supervision is the kind of depth that is good for our method too. But yeah, I think that's really interesting.
Thank you.
On a related question, Noah, how much 3D do we need? The relative ordering, is it enough, or do you think we need to go further in the 3D representation?
Ultimately, yes. The way that I kind of got into this is that at the end of the day, I still want to be able to lift any video to metric 3D. And so this 2D correspondence is sort of like a first step towards that. If you get the 2D correspondence, maybe then the 3D lifting becomes easier. But I'm still not sure. I don't know if we're doing it right. It could be that we should be estimating 2D correspondence and lifting it to 3D, like I just said. But maybe it would be better to estimate everything together, even if that's super ill-posed. Maybe it's the right thing to do, just from a I don't know, first principles. It seems like these things are all related, so maybe we should estimate them all at the same time. So we took one approach here, but I'm honestly not sure if it's in the end going to be the right one for if your goal is to estimate 3D, metric 3D from videos.
And
I comment. Can I make a comment?
Go ahead, Hocam.
There was a paper in the 1990s by Ed Adelson from MIT. The title of the paper was Representing Moving Objects with Layers. So they actually segmented these different objects into different layers, and they assumed each layer is planar. They just ordered the layers. So this work, just reminded me that early work by Adelson. Of course, this is much more improved, but I just want to make that comment.
Yeah, I know. I'm a big fan of that work. And sort of that's one of the, I mentioned this multiplane images representation, which is also very much related to that layered representation. But yeah, I think the key question, I think one of the key questions has been how to extend that to things that move, because even in their videos, the motion is induced by the camera motion and not by the like scene itself deforming like people do.
But there was occlusion in that work. I
That's
remember. So they were able to handle occlusion by these layers.
That's a good point. Yeah. But if something's moving, then it becomes more complicated because, if the scene is static and the camera's translating, then things that move faster are also things that are closer to the camera.
Yes.
But if the things that are close to the camera are also moving in the opposite direction, then that like assumption no longer holds true. Like something could be staying still, but be the closest thing to the camera because it just happens to be moving exactly in the same direction as the camera.
Yes.
But yeah,
Thank you.
I think, yeah, I like that. I think there's a lot of like really good ideas in these classic papers.
Okay, one last question. Noah, what do you
Sure.
think of semantics here? Do you think we should move the objects from points can be, or is there any benefit?
I mean, I feel like it's inevitable. I mean, it just feels like the whole vision community is going towards like everything will be sort of done at once in some huge like foundation model. I mean, it's a bigger maybe philosophical question than what you're asking, but I feel like it just feels like the way things are moving, everything is going to be sort of unified together somehow. But which was depressing because it's like I don't know how to I don't know what my role will be in that, because that's just like big industry forces are barreling towards that. Sorry.
Impressive contributions like you presented today. Thank you very much, Noah. This was a great.
Thank you so much. Yeah. Okay, great seeing you all. Thank you very much. It was really a pleasure to talk to you.
See you, Noah. Bye.
Yep. Bye-bye.